So in this video, which covers section 2-3 in the textbook, we want to talk about another specific kind of motion that is projectile motion. So if you think about throwing a football or launching a rocket or something like that, this is something that's just acted on by gravity, and we want to find or understand the kinematics of that kind of motion. So we just have a simple model for this. We'll ignore things like drag forces, and we'll be able to make or derive some pretty general formulas for this kind of motion. So our textbook example in this case is a launching of a pumpkin. So you somehow use some kind of trebuchet or some other device to throw a pumpkin. So we create a coordinate system x, y here, and we launch the pumpkin with some initial velocity v naught at some angle beta measured from the x-axis. And then we want to know things like how far does it go before it hits the ground, how long does it take, that sort of thing, and all that can be derived with what we've learned so far. So the basic assumption here is that the only force acting on this is gravity, and the gravity is in the y direction, so along this unit vector j. Okay, so we have some path on which it travels. In general, there will be a drag force, right? So there's air resistance whenever you throw a pumpkin or anything else, and that acts opposing the motion. So if the pumpkin is flying this way, the drag force would be tangent to the path and opposing the motion, but we're going to ignore that. Okay, so if that's the case, the only force on this is the gravity. It acts vertically. There's no horizontal force, so there's no horizontal acceleration, so there's no change in the horizontal velocity, right? So the sum of the forces on this pumpkin are just gravity, which is mg, and it acts in the y direction, so it's proportional, it's multiplied by j hat, the unit vector in the y direction, and it's negative because y is measured up and the gravitational force is down. Okay, so um, we write F equals ma, so the only forces are minus mg j hat, and this equals ma, which is the mass times the acceleration written here in terms of the x component of the acceleration times I hat plus the y component of the acceleration times j hat. And because there's no forces in the x direction, then ax will be 0, and there's no change in the x coordinate, x component of the velocity, and then ay will be proportional to the gravity, right? So ax is x double dot, ay is y double dot. So our two differential equations governing this projectile motion is that x double dot is 0 because there's no forces in the x direction, and y double dot is minus g because the masses cancel, and so the acceleration in the vertical direction is minus g. So we can just solve those two differential equations. We integrate x twice, we get x of t. The time-dependent position is the initial position in the x direction plus the initial velocity in the x direction times t minus t naught plus 1/2 times 0 because there's no acceleration in the x direction, so that just goes away. If we assume t naught is 0 and vx of 0 is the x component of the initial velocity, so v naught is the initial velocity, but it's at an angle beta. So the x component of the initial velocity is v naught cosine beta. And so x of t is just v naught cosine beta times t. So the position just increases linear in time, which is consistent with the fact that there's no acceleration. Okay, so similar in the y direction, we integrate a couple times, but we keep this quadratic term because there is acceleration due to gravity. Again, the y component of the velocity is v naught sine beta. We assume t naught is 0, y naught is 0, so y of t is v naught sine of beta t minus 1/2 gt squared. Okay, so because of this, we get this parabolic trajectory for the motion. Now, to find the trajectory itself, we can solve for time in the horizontal equation, and then derive an equation for y as a function of x, and that gives us our trajectory independent of time. And we can write it this way: y is tangent of the launch angle beta times x minus g secant squared beta over 2v naught squared x squared. Okay, and that gives us the parabolic trajectory we would expect. All right. This is a general result, so any projectile, when you ignore drag forces, is going to be a parabolic trajectory. Okay, let's just do a couple examples to lay this out. Okay, so here's the first one. We're shooting, say, a bullet or something at a target. Okay, so we have a particle launched from the origin at a speed of 1100. This is not written correctly. There's a typo here. It's 1100 feet per second. And we're trying to hit a target at this end. And the target has some vertical extent. And so the question ultimately is, what are the range of angles that would allow us to hit that target, right? So if we aim a little high, we'll hit the top of the target. And if we aim a little lower, we'll hit the bottom of the target. And so the question is, what are the range of angles that would allow us to hit the target? All right, so we're launching at a high speed, 1100 feet per second, and we're aiming at a target which is 1,000 feet away. So it only takes about 1 second for the projectile to get the target. The bottom of the target is 4 feet above the ground. The top of the target is 7 feet above the ground, or the height of the target is 3 feet. And they want to know this range of angles. So we can write down the relevant equations. The horizontal position is the initial position, which we'll ultimately assume is 0, times v naught x, the x component of the initial velocity, times the final time, okay, where we say tf is the time at which the projectile gets to the level of the target. And then the vertical position is y naught plus v naught y, the y component of the initial velocity, times tf minus 1/2 gtf squared. We assume the initial position is 0, that we're launching at the origin. Here's the initial x velocity, the initial y velocity, and then the final position is a distance r from where we launched, right? R is the distance it travels here. So the initial x position is 0, the final x position is r. The initial y position is 0, the final y position is either h1 or h1 plus h. Okay, so we can treat this a vertical position when the target gets a distance r from when the projectile gets a distance r from the initial launch point. Okay, so yb is our unknown height, and we can write that r then, with setting xb equals r is v naught tf cosine theta, and yb is v naught tf sine theta minus 1/2 gtf squared. Okay, we can solve this by eliminating the final time, and we get yb is r tangent theta minus gr squared over 2v naught squared secant squared theta. So that relates theta to yb. So we have two values of yb, and for each of those we can solve for the angle. Now we can do a little simplification just with trigonometry, rearrange it, and we get a quadratic equation for the angle. So for the tangent of the launch angle is a function of the initial velocity, the distance from the launch point to the target, and then the height at the end. All right, now because this is quadratic, there's two solutions. So for each, for example, if we're just looking at a projectile that hits the top of the target, there's two solutions. And then for the bottom of the target, there's two solutions. So there's actually 4 angles that we're interested in. Now, why is that? Well, so it turns out there's 2 ways to hit this target. One is to launch at a very shallow angle and aim essentially directly at the target. So a very low value of theta. And the other is to launch almost vertically and have the bullet go, or the projectile go very high and then come down and hit the target. So in that case, theta is almost 90 degrees. So there's two ways to hit this target. If we do the math, then to hit the bottom of the target, that is a height of 4 feet, we get an angle here of about 1 degree, and then here, 89 degrees. And then to hit the top of the target at 7 feet, we do either a little over 1 degree or again almost 90 degrees. And notice how close these are. This is 89.23747, and this is 89.23750. So we have to be pretty precise to be able to aim vertically or nearly vertically and hit that target. So clearly that's not what you'd want to do. If you really want to hit the target, you'd want to use these small angle approaches and aim almost directly at the target, not straight up in the air. Okay, so that's what this goes through. I don't need to go through this. You can look at it later if you want to. Just as a gut check, they looked at what are the angles to aim right at the top and bottom of the target, and it's of the order of what we're looking at. You can look at this later if you want. Okay, so let's do one more example. This is a baseball problem. So a batter hits a ball 4 feet above the ground and hits it hard enough that it just clears the wall out in center field, which is 400 feet away and 9 feet high. So the question is, how hard do you have to hit the ball? That is, what is the velocity of the ball coming off the bat and the angle such that it just clears the wall? Okay, so it's the same kind of analysis as what we just did. The x position is the initial position plus the initial x velocity times t. The y position is the initial y plus the initial y velocity times t plus 1/2 ayt squared. Okay, so if we put in some values, we assume x naught is 0, y naught is h, and then we have v naught cosine theta for the x component of velocity, v naught sine theta for the y component of the initial velocity, and then g for the acceleration, right? So we can solve these two equations here on the right for the initial velocity, and we get this. V naught is d square root of g over this mess. Okay, so that tells us the velocity we need to fire this at as a function of angle. And it turns out there's an infinite number of solutions. Okay, so it's a continuous solution, and this is a plot of the initial velocity required as a function of the launch angle, right? So if we have a very low angle and aim low, we have to shoot at a very high velocity to get it to clear the wall, and that's unrealistic. There's only so much velocity a typical batter can impart. And similarly, if you shoot very high, if you shoot at a high angle, straight up in the air, you have to use a very high velocity to get it to the wall. And the minimum velocity needed is actually at 45 degrees. So the ideal launch angle is 45 degrees. And then it looks like the velocity is what, about 100, maybe 150 feet per second at 45 degrees to clear a 9-foot wall at 400 feet. All right, so that's how you do these projectile problems.